Today we're going to be learning about stoichiometry. Do you have any guesses on what this topic is about? No worries, let's break it down. The most recognizable part of this word is metry. It sounds like meter, doesn't it? So by inductive reasoning, this suffix means the process of measuring. If we take it a step further and look at the Greek word it originates from, metron, we find that this root means to measure. But to measure what? Well, let's go back to the prefix, stoichio. It originates from the Greek word stoichion, which means elements. Without much thought, we might think it's the study of measuring elements, and in essence, it is. But before we dive into the topic, I want you to give this a chance to blow your mind. First, picture how understanding chemistry will give you a deeper knowledge and appreciation of the uniqueness of your world. You see, chemistry holds the secrets to how life first formed, how the materials we use from iPhones to couches are created, how diseases are cured, and how your body manages to continuously and simultaneously have the capacity for billions of chemical reactions to carry out on their own every minute. And for scientists to understand all these processes, they first need to have a good grip on stoichiometry and its rules. Maybe it's just me, but I feel like my ability to enjoy the world is directly correlated to how I can picture what we can't see with the naked eye. It's incredible how three tiny particles, the proton, neutron, and electron, come together in trillions of combinations to make up everything we can see. Chemistry explains everything you can touch, how it feels, and why it behaves the way it does. Truly, by describing everything that you cannot see. What I'm trying to say is these elements we'll be working with are the building blocks of mass, and therefore matter. They matter. Here's a question for you. From smallest to largest, in what order do these next words go in? Molecule, particle, element, and compound. Yes, so we can't have the latter without the former. So here we see particles making up elements, elements in conjunction with other elements making up molecules, and these molecules connected by chains to yield compounds. The further down the line we go with this increasing in size, in a biological perspective, let's say tissue, organ system, organisms, and so on, you can see that it's easier for us to personally connect to chemistry and understand the world the larger it is. So how do we weigh something we can't even see? Surely we must have some sense of how much of that object there is to predict how it will act, and that is why we have the study of stoichiometry, the science of measuring the quantity of chemicals that react and are byproducts of any given reaction. And yes, I will be giving you a heads up. There will be math involved, but the great news is it's the most basic concepts of math, like adding, subtracting, multiplying, and rarely dividing. The most extreme algebra we'll do is a sort of balancing of equations. But I feel like this is very reasonable, considering that this is how we decode what we can't see into what we can. Now let's start. Can you give me some examples of your favorite foods that your mom cooks? You see how what she serves on your plate is just a finished product of either physical or chemical reactions she concocts in the kitchen, but regardless, you know it's the same initial ingredients, just not in the same form. Aren't moms amazing? They are truly unrecognized scientists. Before moving on, I want to highlight a key concept I just mentioned. I want you to be able to differentiate between a physical and a chemical reaction. Can you give me some examples of a chemical reaction you might see your mom or a baker or a chef make in the kitchen? How about a physical one? Yes, so mixing dry elements does not alter them individually. For example, when mixing flour and chocolate chips, you can always use a colander to separate them and end up with the original ingredients. However, what would you consider a scrambled egg? Yes, a chemical reaction. There's no possible way, even if the chicken begs for its baby back, will we ever be able to get the original phase of the uncooked egg. Can you tell me a key difference in these two processes? Yes, so in one we applied heat. And we can see that heat can be a part of the reactants, but it can also be a product. And although heat is a good indicator that a chemical reaction took place, it is not always the case. If we were to melt a chocolate chip, it would change the physical phase from a solid to a liquid. And maybe it doesn't hold its original shape, but ultimately the chocolate did not change chemically. And under the right circumstances, this isn't necessary, but if I had the same mold, I could get the original shape back and therefore the original ingredient. So, like I previously explained, with the whole cooked scrambled egg example, a good indicator that a chemical reaction has taken place is when bonds have been broken and new ones have been formed. This creates an exothermic or an endothermic reaction, which we will get to later. Are there any chemical or physical reactions that come to mind now? Now that we get reactions out of the way, let's head back to mass. In order for us to see these infinitely small reactions take place, we have to manipulate the initial variables into more tangible measurements. Otherwise, we would be stuck measuring elements in their atomic mass unit, and that is an arbitrary unit of measurement that we kind of just came up with to make it easier to measure single atoms. And I'm so seriously not kidding. 1 AMU is a 12th of the mass of an atom of carbon-12. And all the elements just have derivative measurements. This is called the relative atomic mass. We find it by averaging the atomic mass of all the naturally occurring isotopes of a given element based on how common that isotope is on the planet. What is an isotope? If you don't already know, it's when an element has the same amount of electrons and protons as expected, but a different amount of neutrons. For example, carbon has a relative atomic mass of 12.01 AMU because there are carbon-12, carbon-13, and carbon-14 isotopes. However, the most predominant one is carbon-12, and therefore skewing the atomic mass closer to 12 AMU. But since AMU is impractical, it's why moles are preferred. Because we cannot see a single molecule, the science community agreed it would be much more ideal if we could work with a group of them and consider them as one whole. This is where moles come in. It's a funny word, but no, I'm not talking about the ones on your face or your back. This is a specific type of mole. Back in the 1800s, a single scientist, whose last name was Avogadro, found out that equal volumes of gas under the same conditions all had an equal amount of molecules. This amount was 6.022 times 10 to the 23rd. It is also believed to be true that in 12 grams of carbon, 12, there are also 6.022 times 10 to the 23rd molecules. This is a key concept in stoichiometry, a key unit of measurement when talking about reactions, because sometimes we don't have the whole mole. So we need to have this middleman to help us turn amount of molecules into grams. Mass, something that we can understand, grip, and measure, or vice versa. Avogadro's number allows us to express a chemical relative atomic mass in terms of grams. It allows us to weigh them, where once a single atom of carbon was 12 AMU, we can calculate that a mole of carbon weighs 12 grams. This is now known as a molar mass. So the amount of molecules is the same in a mole of anything, of everything, of any other element, but the weight varies depending on the relative atomic mass of the element. Can you help me solve for the weight in grams of the mole of oxygen? Make sure your units are intact. Great, that is known as the molar mass. And it's important to know that moles are a standard unit of measurement. So let me ask you another question. If I were to tell you that your school had a mole of soccer balls, how many soccer balls does your school have? Now that sounds like the most fun you kids could ever have, but Avogadro's number is so large that those soccer balls could potentially take up the whole surface of the continent. So maybe not so fun when you can't even watch TV because there are soccer balls stacked up all throughout your house. Just so I can make sure you're all caught up, have you ever been exposed to scientific notation in your math classes? That's okay. Let's break it down and work with small numbers. If I had 20 soccer balls and I wanted to put it in scientific notation, I would have to move the decimal to the left once. The reason for this is scientific notation requires for the number before the x to be in between 1 and 10. So this would look like 2.0 times 10 to the first power of soccer balls, of course. This just means that you need to multiply 2 once by 10 in order to get your original notation, which was 20 soccer balls. These two numbers, although they look very different, are one and the same. Next example. This one I'm going to have you work out by yourself. Please write 80 times 10 to the 23rd in correct scientific notation and 0.8 times 10 to the 23rd also. Can you think of a reason why we might use this notation? Right, because the amounts we're working with are so large, it's faster and easier. Let's say it's a shortcut to writing it out. You see, a key concept here to remember is any number you write in any science class must be immediately followed by a unit, whether it's grams, molecules, or even elephants. But a standalone number in science does not exist, and if you were to ever look back on your notes, it would be confusing. So although it's faster to leave out the unit of measurement when working out a stoichiometry problem that requires math, it's highly advised not to, and will most likely get you points docked from your quizzes if this happens. And now that we know how to find the molar mass of elements, we can now calculate the molar mass of compounds. All that is needed to find the answer is adding up the molar masses of its components. So for instance, if the molar mass of hydrogen is 1.007 and oxygen is 16, the molar mass of H2O would be, this is where the units of measurements are going to become necessary to explicitly write, so you don't get confused. So because there is 1 mole of H2O, that means that each H2O molecule has 2 hydrogen atoms and 1 oxygen atom. Therefore, there are 2 moles of hydrogen and only 1 mole of oxygen. Now you multiply the number of moles of each element by the molar mass and add them up, and you'll have the molar mass of the whole compound. Moles not only help us decipher the weight of each compound, but help us balance equations out. If we look at this photosynthesis equation, we see that carbon dioxide and water break down with the help of sunlight to create glucose and oxygen. Although the bonds in each compound have broken, the amount of moles of each element are required to be balanced on both sides of the equation. This is the law of conservation of mass. It may not look like much of an equation, but the arrow can be loosely compared to the equal sign you see in math. If the arrow points in both directions, then it is almost indistinguishable from the equal sign you might find in algebra, because the reaction with the help of heat or a catalyst can easily make the reaction go in either direction. Without balancing the equation, we have a useless piece of information because it doesn't give us much to interpret. The way we balance it is by starting with the longest or most complicated molecule, which in our case would be the glucose molecule, on the right side. In order for it to be a true glucose molecule, there must be 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. Now we go back to the left side, multiply carbon dioxide by 6 and the water molecule by 6 so we can balance the equation out. And now we are left with a surplus of 6 moles of oxygen, which will now be the coefficient on the oxygen on the right side of the equation. Having them in the lowest divisible number is incredibly useful in helping us understand the proportions of chemicals as they react on the molecular level for observation or even future replication. But in the real world, we deal with the mass or weight of substances and not in the amounts of each. So the last thing we would need to consider is to calculate the specific masses. This is where Avogadro's number comes into play. Head and keep working with the photosynthesis example. Now let's assume that there is only 1 gram of available carbon dioxide in the nearby air. How much glucose will be yielded by 1 plant? Now let's start off with our known variables. 1 gram of carbon dioxide, and we'll be searching for glucose. Because we will be working with these 2 molecules, it is safe to assume that we will be needing their molar masses to convert from moles to grams and grams to moles. So I went ahead and solved for their molar mass. As you may know by now, in order to solve for a molecule's molar mass, you must find the molar mass of each component and multiply it by the atoms in that molecule, add them up, and that's how you get your molecule's molar mass, which is what we see here with carbon dioxide and glucose. Although glucose's equation looks a little bit more extensive, I promise you it is the same process. Let's move on to the balanced equation we worked on. 6 moles of carbon dioxide plus 6 moles of water, aided by sunlight, yield glucose, 1 mole of glucose, and 6 moles of oxygen. Now let's solve. Here we're going to start off with our known variable, 1 gram of carbon dioxide. I went ahead and put it over 1 just to be aligned with our fractions. As you may know, any whole number over 1 is the same whole number. In order to cross out the grams of carbon dioxide and change from one unit of measurement to another, we must cancel it out as you would unknown variables in math. Let's say you have 3x over x. You cross out the x's and you're left over with 2x. This is the same concept. Here you see that I flipped the molar mass in order to cancel the units like we just mentioned. I like to go ahead and work through my problem before solving anything in my calculator, so everything's a little bit more straightforward and I understand the trajectory of the solution. As you can see, I was able to cross out grams of carbon dioxide, and now we're working with moles of carbon dioxide. In order to switch from moles of carbon dioxide to moles of glucose, we must do a simple ratio that we get from our chemical reaction. As you see, 6 moles of carbon dioxide yield only 1 mole of glucose. Now, I will be inputting glucose's molar mass, and this time I keep it in its same format because this is how I will be able to cancel out moles of glucose and end up with grams of glucose, which is what we are looking for. Now, once you input it into the calculator, you multiply 1 with 180. You go all the way across and see that those are the only ones on the numerator. And then you divide by the denominators, which is by 44 and by 6. You divide individually and you will get an answer of 0.682 grams of glucose. One thing to notice here is the arrow pointing in one direction. It's important to note that if you want to give off that a reaction goes in both directions, you must put an arrow going in each direction. And the length of the arrow can also indicate the most common reaction. So if the arrow that's pointed to the right is longer than the arrow pointing to the left, it will insinuate that the forward reaction is a lot more potent than the backwards reaction. As you can see through this beautiful piece of art called conversions, there will only be 0.682 grams of glucose produced per 1 gram of carbon dioxide. One thing I would like for you to take away is the setup I have shown you. First, on the left, we write out all of our known variables. In the next column, we write out our equations. In the final one, we fill out the equation with the known variables. And the last column is for your answer. I hope you don't feel it's redundant and see the potential this organized problem-solving technique can have on other subjects, especially top math courses and physics. I hope today was helpful for you in your trajectory as a scholar. It was equally as enjoyable for me to be there for you.